Fancy A, or you can say this cursive A, is an open cover of A, hence can be reduced to a finite subcover because A is a compact set. Finite subcover, say, let's suppose that finite subcover is G1, G2, say up to Gn. It's a finite subcover of A. So let H1, H2, let H1, H2, Hn be the class of open sets, class of open sets corresponding to these open sets, corresponding to the class of open sets G1, G2 up to Gn, and they are disjoint because Gx and Hx are disjoint by disjoint open sets here, Gx, Hx. So we have here G1, G2, Gn and H1, H2, Hn. So then they are disjoint in like this. Hi intersection Gi is 5 for all 1 less or equal to I less or equal to n, and this A, it is subset of union Gi, I runs from 1 to n, and second these Hi's, they are subsets, they contain B is subset of Hi1 less or equal to I less or equal to n. Okay. So it's this because of this property, and Gx and Hgx contains X, Hx contains B, so they are disjoint open sets, and in this way we have a class of open sets Gx, X belongs to A, and this is an open cover of A. This class cursive A, it's an open cover of A, hence can be reduced to a finite subcover, say G1, G2, Gn, and let's take these H1, H2, Hn be the open sets corresponding to these open sets G1, G2, Gn. Then they are disjoint because Gx and Hx are disjoint open sets, so Hi and Gi, they are disjoint. Now this A, it's subset of union Gi I runs from 1 to n because Gi I runs from 1 to n is a cover of A. It's a finite subcover of A. So A is subset of this, and B is subset of each Hi. So this gives this A is subset of G, and B is subset of each Hi. So it will be subset of intersection Hi, I runs from 1 to n, that will denote by H. So G and H, they are open sets, so thus they are also disjoint, thus G and H are disjoint open sets such that A is subset of G and B is subset of H. So hence X is a normal space, hence X is a normal space. X is a normal space. So that proves this result. X is a normal space. So next we have an important lemma that's called Urysohn's lemma. It's very important and very interesting lemma, Urysohn's lemma. And I hope you will enjoy this lemma. So to prove this lemma, we first prove the following lemmas. So let's first prove those lemmas, then we state Urysohn's lemma, and then we'll write its proof. Okay. So let's first prove this lemma. Lemma number 1, okay, which we are going to use in Urysohn's lemma. Let X be a T1 space. X be a T1 space. Then X is regular if and only if for all x belongs to x and a neighborhood u of x, there exists a neighborhood v of x such that x is in v, because v is a neighborhood of x, v is subset of v closure, that's trivial, but this is important, this v closure is subset of u. So for any neighborhood u of x, we can find a neighborhood v of x such that v closure is subset of u. That's first lemma. Let's prove this lemma. So we first assume that X is a regular space, and we'll show that for any open set, let's first assume that X is a regular space. We assume that X is a regular space, and we'll show that for any neighborhood u of x, there exists a neighborhood v of x such that v closure is subset of u. Proof. Assume X is a regular space. X is a regular space. So we assume X is a regular space, and we will show that for any neighborhood u of x, there exists a neighborhood v of x satisfying this property. So let's take any neighborhood u of x. Let u be any neighborhood of x. So then x is in u. This implies x is not in u complement. Let's write this as b. And b is a closed set, and b is a closed set. B is a closed set. Now, from the definition of a regular space, this B is a closed set and X is not in B, then we can find two disjoint open sets. So here it's suppose this is our space, which is a regular space, and that's suppose U, and X is here, X is a point in U. And this is U complement, that we denote by B. This B is a closed set because it's the complement of open set, U is open. Okay, so that's the set B, which is equal to U complement. So B is closed set, and B is a closed set, and X is not in B. Since X is a regular space, X is a regular space, therefore X and B can be separated by disjoint open sets. By disjoint open sets, say V and W. Say V and W. That is, X belongs to V and B is subset of W. So B is subset of W. So W is like this. W is bigger than B. This is this whole is W. Okay, this is W, and V is somewhere here. They are disjoint. This is V. Okay. So V and W, they are disjoint open sets such that X is in V and W contains V. That's the definition of a regular space, because X is a regular space. So now we show that B and V there, B and V closure. Now we show that B intersection V closure is the phi set. They are disjoint. The closure of V with B, it's a null set. So we show that any point which is in B is not in B closure. So let's choose any point. Let Y belongs to B. Okay, we show that Y is not in B closure. Y is not in. This will show. This will prove. Okay, if we prove this, it means that B and V closure, they are disjoint. Their intersection is the empty set. So clearly this Y cannot be in V because it's in B. It's in B. It's in B. And V and W, they are disjoint sets. V and W, they are disjoint. And Y is in B. So B is this set. So it means that B and V are also disjoint. B and V are all, because B and W are disjoint and W is bigger than B. B and V, they are disjoint sets. Actually, V and W are disjoint sets. V and W are disjoint sets here because they are separated by two disjoint opposites, V and W. V and W, these two sets, they are disjoint. So it means that V and B, they are also disjoint because B is smaller than W. Let me write it here. As V intersection W is empty set, this implies V intersection B is also empty, as B is subset of W. B is subset of W. So it means that Y is not in B because Y is in B. Y is in B, therefore Y cannot be in B. Now we show that now we show that Y is not in V closure. So far, if Y is in V closure, since Y is not in V, it's in V closure, therefore it's like it's a limit point. So then every neighborhood of Y intersects with V. Every neighborhood of Y intersects with V. Okay? Every neighborhood of Y. As Y is in B, since Y belongs to B, B is subset of W, therefore W is a neighborhood of Y. And here every neighborhood of Y intersects with V. So this implies W is a neighborhood of Y. This implies W intersects with V, a contradiction because V and W are disjoint. Here, a contradiction. So it implies that B intersection V closure is the empty set. B intersection V closure is the empty set. So from this we conclude that V closure is subset of U, and this implies X is already in V. V is subset of V closure. It is always true because V closure is the smallest closure set containing V, and V closure is subset of U. Now let's verify this, how this V closure is subset of U. So there it's a set U which contains a point X. Okay, this is set U, and this is U complement. This one, it's U complement. Yeah. It's U complement, which is our B. U complement. Okay. Now we have two disjoint open sets. One is V and second is W. So that's V, and that's W. W contains B, so W is like this. It is bigger than V. So that one, that whole, this is W. V and W they are disjoint sets. V contains X and W contains B. Now this B intersection V closure, B and V closure, B is up to this portion, this region is B. Its intersection with V closure is the phi set. They are disjoint. So it implies that V closure must be in U, because U is this whole set. This is U. So it means that V closure must be subset of U. Every element of V closure should be in U, because for if suppose there is an element in V closure which is also in B, which is not true, because B and V closure, they are disjoint sets. So any element of U should be the member of any member of V closure. V closure V is this. V closure is bigger than this. It's bigger than this. This is V closure. Any member of V closure must be the member of U. For if possible, there is a member of V closure which is not the member of U, then that member must be the member of B, because that member must be outside of U. So outside of U means it should be in U complement of Z. So any member which is in V closure, for if possible that member is not in U, then that member must be in U complement, which is V. So that means that member must be in B. So which means that B and V closure, they are not disjoint, which is a contradiction, because they are disjoint sets. So that means every member of V closure must be the member of U. So which means V closure is subset of U. So that means X belongs to V. V is subset of V closure and subset of U. So this proves the one way. Now we prove its converse part. Now we prove its converse part. Conversely, assume that for any x in X and for any neighborhood, for any neighborhood V of X, there exists a neighborhood U of X such that X belongs to V, subset of V closure, subset of U. Suppose this is true. So this is the lemma. So in first case we have assumed that X is regular and we have shown this property. Now we conversely assume that suppose this property holds for any neighborhood U of X, there is a neighborhood V of X such that X belongs to V, subset of V closure, subset of U. So this we assume. Okay, that's our assumption. Now we show that X is regular. We show that X is regular. Regular means any point and any closed set which does not contain that point can be separated by disjoint open set. So let's take any closed set. Let B be any closed set and X belongs to X such that X is not in B. And we need to show that they are separated by disjoint open sets X and V. We need to show that X and B can be separated by disjoint open sets. So then X, it's not in B, therefore it is in B complement. So therefore, and B complement is an open set, so which implies B complement is a neighborhood of X. And here it is given that for any X in X and for any neighborhood V of X, there exists a neighborhood U of X such that this holds. And here B complement, it's a neighborhood of X. So therefore there exists a neighborhood V of X such that X belongs to V, subset of V closure and subset of V complement. V closure is subset of V complement. So let's take this V closure. This is suppose space. That's suppose B. That's B. That's V complement, and V closure is bigger than V complement. This is a V closure. This one is V closure. This is V closure. Okay. Now, what's the complement of V closure? The complement of V closure. It's so here it's V closure is sorry, oh sorry, V closure is subset of V complement, not V closure contains V complement. So that's a space X, that's B, this is B, and this is B complement, and B complement contains V closure. So this is V closure, okay? This is V closure. V closure contains B complement. Now what's complement of V closure? It contains B because complement of V closure holds this portion. That's complement of V closure. Then B is subset of V closure complement, and X belongs to V, and both are open sets because V closure is closure, its complement is open. Its complement is open. So that means they are both open sets, V closure complement and V closure complement contains B, and V contains X, and they are also disjoint, and V complement closure intersection V is the phi set. You can easily verify this. That's an open set, that's a neighborhood which contains V, and that's a neighborhood V which contains X. So which means that X is a regular space, because for any closed set B and any point X which is not in B, these two X and B can be separated by disjoint open sets X and B. They are separated by disjoint open sets V and V closure complement. So hence the converse part follows. Now we prove second lemma. And then we come to Urysohn's lemma. Okay. Lemma number 2. Lemma number 2. Let X be a T1 space. X be a T1 space. T1 space means each singleton set is closed. That's already done. Then X is normal. Then X is normal if and only if. So normal means any two disjoint closure sets can be separated by disjoint open sets. That's normal. X is normal if and only if given a closure set A and an open set U, if and only if given a closure set A and an open set V, and an open set V containing A is subset of V. Containing A, it's actually general case of this, because here we have seen that given any X and given any neighborhood U of X, so X belongs to U, and here we have a set A is subset of, instead of a point we have a set here containing A